Are we ready?
Hey, Alan. Oh, that's
Okay, ready to start? Ready for the taping to start in a minute. He's going to raise his hand and signal that I'm on. Just a minute though. Let him settle. Okay, guys. Okay, give me the signal then when you want me to start. Okay, this is Linear Algebra Lecture 4, and the first thing I have to do is something that was on the list for last time, but here it is now. What's the inverse of a product? If I multiply two matrices together, and I know their inverses, how do I get the inverse of A times B? So I know what inverses mean for a single matrix A and for a matrix B. What matrix do I multiply by to get the identity if I have A? Okay, that'll be simple but so basic. Then I'm going to use that I will have a product of matrices, and the product that we'll meet will be these elimination matrices, and the net result of today's lecture is the big formula for elimination. So the net result of today's lecture is this great way to look at Gaussian elimination. We know that we get from A to U by elimination. We know what the steps, but now we get the right way to look at it, A equal LU. So that's the high point for today. Okay, can I take the easy part, the first step first? So, suppose A is invertible, and of course it's going to be a big question, when is the matrix invertible? But let's say A is invertible and B is invertible, then what matrix gives me the inverse of AB? So that's the direct question. What's the inverse of AB? Do I multiply those separate inverses? Yes. I multiply the two matrices A inverse and B inverse, but what order do I multiply? In reverse order. And you see why. So that the right thing to put here is B inverse A inverse. That's the inverse I'm after. We can just check that AB times that matrix gives the identity. Okay. So why? Once again, it's this fact that I can move parentheses around. I can just erase them all and do the multiplications any way I want to. So what's the right multiplication to do first? B times B inverse. This product here is the identity. Then A times the identity is the identity, and then finally A times A inverse gives the identity. So, forgive the dumb example in the book. It's just why do you do that inverse things in reverse order? It's just like you take off your shoes, you take off your socks. Then the good way to invert that process is socks back on first. Then shoes. Sorry. Okay, I'm sorry that's on the tape, but and of course, on the other side, we should really just check on the other side. I have B inverse, A inverse. That does multiply AB, and this time it's these guys that give the identity. Squeeze down, they give the identity. We're in sync. Okay, so there's the inverse. Good. While we're at it, let me do A transpose. Because the next lecture has got a lot it involves transpose. So if I transpose a matrix, I'm talking about square invertible matrices right now. If I transpose one, what's its inverse? Well, the nice formula is, let's see, let me start from A inverse equal the identity. And let me transpose both sides. That will bring A transpose into the picture. So if I transpose the identity matrix, what do I have? The identity, right? If I exchange rows and columns, the identity is a symmetric matrix that doesn't know the difference. If I transpose these guys, that product, then again it turns out that I have to reverse the order. I can transpose them separately, but when I multiply, those transposes come in the opposite order. So it's A inverse transpose times A transpose, giving the identity. So this equation is just comes directly from that one. But this equation tells me what I wanted to know. Namely, what is the inverse of this guy's A transpose? What's the inverse of that? If I transpose a matrix, what's the inverse of the result? And this equation tells me that here it is. This is the inverse. This is the inverse of A transpose. Inverse of A transpose. Of A transpose. So I'll put a big circle around that because that's the answer, that's the best answer we could hope for. That if you want to know the inverse of A transpose, and you know the inverse of A, then you just transpose that. So to put it another way, transposing and inversing, you can do in either order for a single matrix. Okay. So these are like basic facts that we can now use. So now I put it to use. I put it to use by thinking we're really completing the subject of elimination. Actually, the thing about elimination is it's the right way to understand what the matrix has got. This A equal LU is the most basic factorization of a matrix. I always worry that you will think this course is just is all elimination. It's just row operations. And please don't. It will be beyond that. But it's the right algebra to do first. Okay, so now I'm coming near the end of it, but I want to get it in a decent form. So my decent form is matrix form. I have a matrix A. Let's suppose it's a good matrix. I can do elimination, no row exchanges. So no row exchanges for now. Pivots, all fine, nothing zero in the pivot position. I get to the very end, which is U. So I get from A to U. And I want to know what's the connection. How is A related to U? And this is going to tell me that there's a matrix L that connects. Okay. Can I do it for a 2 by 2 first? Okay, 2 by 2 elimination. Okay, so I'll do it under here. Okay. So let my matrix A be, let's just, we'll keep it simple. Say 2 and an 8, so we know that the first pivot is a 2, and the multiplier is going to be a 4. And then let me put a 1 here. And what number do I not want to put there? 4. I don't want a 4 there because in that case, the second pivot we wouldn't have a second pivot. The matrix would be singular, general, screw up. Okay, so let me put some other number here like 7. Okay. Okay, now I want to operate on that with my elementary matrix. So what's the elementary matrix? Strictly speaking, it's E21 because it's the guy that's going to produce a 0 in that position, and it's going to produce U in one shot because it's just a 2 by 2 matrix. So 2, 1, and I'm going to take 4 of those away from those, produce that 0, and leave a 3 there, and that's U. And what's the matrix that did it? Quick review then. What's the elimination elementary matrix E21? It's 1, 0, thanks, and negative 4, 1. Right. Good. Okay. So that, you see the difference between this and what I'm shooting for. I'm shooting for A on one side and the other matrix is on the other side of the equation. Okay, so I can do that right away. Now here's going to be my A equal LU, and you won't have any trouble telling me what. So A is still 2187. L is what you're going to tell me, and U is still 2103. Okay, so what's L in this case? Well, first, so how is L related to this E, guys? It's the inverse, because I want to multiply through by the inverse of this, which will put the identity here, and the inverse will show up there, and I'll call it L. So what is the inverse of this? Remember that those elimination matrices are easy to invert. The inverse matrix for this one is 1, 0, 4, 1. It has a plus sign because it adds back what this removes. Okay, so if we did the numbers right, we must. This should be correct. Okay, and of course it is. That says the first row is right. 4 times the first row plus the second row is 87. Good. Okay, that's simple, 2 by 2. But it already shows the form that we're headed for. It shows, so what's the L stand for? Why the letter L? If U stood for upper triangular, then of course L stands for lower triangular. And actually it has 1s on the diagonal, where this thing has the pivots on the diagonal. Oh, sometimes we may want to separate out the pivots. So can I just mention that sometimes we could also write this as, we could have this 1, 0, 4, 1. I'll just show you how I would divide out this matrix of pivots. 2, 3. There's a diagonal matrix, and just whatever is left is here. Now what's left? If I divide this first row by 2 to pull out the 2, then I have a 1 and a 1/2. And if I divide the second row by 3 to pull out the 3, then I have a 1. So that's if this is LU, this is maybe called LD for pivot U. And now it's a little more balanced because we have 1s on the diagonal here and here, and the diagonal matrix in the middle. So both of those, MATLAB would produce either one. I'll basically stay with LU. Okay. Now I have to think about bigger than 2 by 2. So right now this was just like an easy exercise. And to tell the truth, that this one with the minus sign and this one with the plus sign, I mean, that's the only difference. But with 3 by 3, there's a more significant difference. Let me show you how that works. Let me move up to a 3 by 3. Let's say some matrix A. Okay. Let's imagine it's 3 by 3. I won't write numbers down for now. So what's the first elimination step that I do? The first matrix I multiply it by? What letter will I use for that? It'll be E to what? Because it's the first step will be to get a 0 in that 2, 1 position. And then the next step will be to get a 0 in the 3, 1 position. And the final step will be to get a 0 in the 3, 2 position. That's what elimination is, and it produces U. And again, no row exchange. We will, I'm taking the nice case now, the typical case too, when I don't have to do any row exchange, all I do is these elimination steps. Okay, now, suppose I want that stuff over on the right-hand side, as I really do. That's like my point here. I can multiply these together to get a matrix E, but I want it over on the right. I want its inverse over there. So what's the right expression now? If I write A and U, what goes there? Okay, so I've got the inverse of this. I've got 3 matrices in a row now. And it's their inverses that are going to show up, because each one is easy to invert. The question is, what about the whole bunch? How easy is it to invert the whole bunch? So, that's what we know how to do. We know how to invert. We could take the separate inverses, but they go in the opposite order. So what goes here? E, 3, 2, inverse. Right, because I'll multiply from the left by E32 inverse, and I'll pop it up next to U. And then will come E31 inverse. And then this will be the only guy left standing, and that's gone when I do an E21 inverse. So there is L. That's L, U. L is this product of inverses. Now you still can ask, why is this guy preferring inverses? And let me explain why. Let me explain why is this product nicer than this one? This product turns out to be better than this one. Let me take a typical case here. Let me take a typical case. So I have to do 3 by 3 for you to see the improvement. 2 by 2, it was just 1 E, no problem. But let me go up to this case. Suppose my matrices E21, suppose E21 has a minus 2 in there. Suppose that, and now suppose, I'll even suppose E31 is the identity. So I'm going to make the point with just a couple of these. Okay, now this guy will have do something, now let's suppose minus 5. 1. Okay, there's 10. That's a typical case in which we didn't need an E31. Maybe we already had a 0 in that 3-1 position. Okay. Let me see if that's going to be enough to show my point. Let me do that multiplication. Okay, so if I do that multiplication, it's like good practice to multiply these matrices. Tell me what's above the diagonal when I do this multiplication. All zeros. When I do this multiplication, I'm going to get 1 on the diagonal and zeros above. Because, what does that say? That says that I'm subtracting rows from lower rows. So nothing is moving upwards as it did last time in Gauss-Jordan. Okay, now so really what I have to do is check this, minus 2, 1, 0. Now this is, so what's that number? This is the number that I really have in mind. That number is 10. And this one is, what goes here? Row 3 against column 2 looks like the minus 5. What? It's that 10. How did that 10 get in there? I don't like that 10. I mean, of course, I don't want to erase it because it's right, but I don't want it there. It's because the 10 got in there because I subtracted 2 of row 1 from row 2, and then I subtracted 5 of that new row 2 from row 3. So doing it in that order, how did row 1 affect row 3? Well, it did, because 2 of it got removed from row 2, and then 5 of those got removed from row 3. So altogether, 10 of row 1 got thrown into row 3. Now my point is in the reverse direction. So now I can do it. Now I'll do below it. I'll do the inverse. Okay, and of course opposite order, reverse order, reverse order. Okay, so now this is the E. It goes on the left side, left of A. Now I'm going to do the inverses in the opposite order. So what's this? So the opposite order means I put this inverse first. And what is this inverse? What's the inverse of E21? Same thing with a plus sign, right? For the individual matrices, instead of taking away 2, I add back 2 of row 1 to row 2. So no problem. And now, in reverse order, I want to invert that. Just this, right? I'm doing this. So now the inverse is, again, the same thing, but add in the 5. And now I'll do that multiplication, and I'll get a happy result. I hope. Did I do it right so far? Yes? Okay, let me do the multiplication. I believe it comes out. So row 1 of the answer is 100. Oh, I know that all this is going to be that, right? Then I have 2, 1, 0. So I get 2, 1, 0 there, right? And what's the third row? What's the third row in this product? Just read it out to me, the third row. 0, 5, 1. Because one way to say is, this is saying, take 1 of the last row, and there it is. And this is my matrix L, and it's the one that goes to the left. It goes on the left of U. It goes into, this is, what do I mean here? Maybe rather than saying left of A, left of U, let me write down again what I mean. EA is U, whereas A is LU. Okay. Let me make the point now in words. The order that the matrices come for L is the right order. The 2 and the 5 don't sort of interfere to produce this 10. In the right order, the multipliers just fit in the matrix L. That's the point. That if I want to know L, I have no work to do. I just keep a record of what those multipliers were, and that gives me L. So I'll draw the so let me say it. So this is the A equal LU. So if no row exchanges, the multipliers, those numbers that we multiplied rows by and subtracted when we did an elimination step, the multipliers go directly into L. Okay. So L is, this is the way to look at elimination. That you go through the elimination steps, and actually, if you do it right, you can throw away A as you create L and U. If you think about it, those steps of elimination, when you've finished with row 2 of A, you've created a new row 2 of U, which you have to save, and you've created the multipliers that you used, which you have to save, and then you can forget A. Because it's all there in L and U. So that's like, I mean, this moment is maybe the new insight in elimination that comes from doing it in matrix form. So it was the product of E's is, we can't see what that product of E's is. The matrix E is not particularly attractive. What's great is when we put them on the other side, they're inverses in the opposite order. There, the L comes out just right. Okay. Now, oh gosh, so today is a sort of like practical day. Can we think together how expensive is elimination? How many operations do we do? So this is now a kind of new topic, which I didn't list as on the program, but here it comes. How many operations on an n by n matrix A? I mean, it's a very practical question. Can we solve systems of order 1,000 in a second or a minute or a week? Can we solve systems of order 1,000,000 in a second or an hour or a week? I mean, if it's n by n, we often want to take n bigger. I mean, we put in more information. We make the whole thing is more accurate for the bigger matrix. But it's more expensive too, and the question is how much more expensive? If I have matrices of order 100, let's say 100 by 100. Let me take n to be 100. Say n equal 100. How many steps are we doing? How many operations are we actually doing and let's suppose there aren't any zeros. Because of course, if a matrix has got a lot of zeros in good places, we don't have to do those operations, and it'll be much faster. But, so just think for a moment about the first step. So here's our matrix A, 100 by 100, and the first step will be that column is got zeros down here. So it's down to 99 by 99, right? That's really like the first stage of elimination. To get from this 100 by 100 non-zero matrix to this stage where the first pivot is sitting up here, and the first row is okay, and the first column is okay. So essentially, how many steps did that take? You see, I'm trying to get an idea. Is the answer proportional to n? Is the total number of steps in elimination, the total number, is it proportional to n? In which case, if I double n from 100 to 200, does it take me twice as long? Does it square, so it would take me 4 times as long? Does it cube, so it would take me 8 times as long? Or is it n factorial, so it would take me 100 times as long? I think, you know, from a practical point of view, we have to have some idea of the cost here. So these are the questions. So let me ask those questions again. Is it proportional? Does it go like n squared, like n cubed, like some higher power of n, like n factorial, where every step up multiplies by 100 and then by 101 and then by 102? Which is it? Okay, so that's the only way I know to answer that is to think through what we actually had to do. Okay, so what was the cost here? Well, let's see, what do I mean by an operation? I guess I mean, well, an addition, yeah, no big deal. I guess I mean an addition or a subtraction or a multiplication or a division. Okay. And actually, what operation am I doing all the time? When I multiply row 1 by a multiplier L and I subtract from row 6, what's happening there individually? What's going on? If I multiply, I do a multiplication by L and then a subtraction. So I guess operation, can I count that for the moment as like one operation, or you may want to count them separately. The typical operation is multiply plus a subtract. So if I count those together, my answer is going to come out half as many as if I count them separately, I have a certain number of multiplies, a certain number of subtracts. That's really what I want to do. Okay, how many have I got here? So, I think, let's see, it's about, well, how many roughly? How many operations to get from here to here? Well, maybe one way to look at it is all these numbers had to get changed. The first row didn't get changed, but all the other rows got changed at this step. So this step, well, I guess maybe, shall I say it cost about, this cost about 100 squared. I mean, if I changed the first row, then it would have been exactly 100 squared, because that's how many numbers are here. 100 squared number is the total count of the entries, and all but this insignificant first row got changed. So I would say about 100 squared. Okay, now what about the next step? So now the first row is fine. The second row is fine, and I'm changing, these zeros are all fine. So what's up at the second step? And then you're with me. Roughly, what's the cost? If this first step costs 100 squared, about, operations, then this one, which is really working on this guy to produce this, costs about, what? How many operations to fix it? About 99 squared. Or 99 times 98, but less, right? Less, because our problem is getting smaller. About 99 squared. And then I go down and down, the next one will be 98 squared, the next 97 squared, and finally I'm down around 1 squared, or where it's just like, just little numbers. The big numbers are here. So the number of operations is about n squared plus, that was n, right? N was 100. It's n squared for the first step, then n minus 1 squared, then n minus 2 squared, finally down to 3 squared and 2 squared and even 1 squared. No way I should have written that, squeeze that in. Let me try it. So the count is n squared plus n minus 1 squared plus all the way down to 1 squared. That's a pretty decent count. Yeah, admittedly, we didn't catch every single tiny operation, but we got the right the right leading term here. And what do those add up to? Okay, so now we're coming to the punch of this question, this operation count. So this is the operation on the left side, on the matrix A, to finally get to U. And anybody, so which of these quantities is the right ballpark for that count? If I add 100 squared to 99 squared to 98 squared, 97 squared, all the way down 2 squared and 1 squared, what have I got about? It's one of these, so let's identify it first. Is it n? Certainly not. Is it n factorial? No. If it was n factorial, we would, with determinants it is n factorial. I'll put in a bad mark against determinants because okay, so what is it? It's n, well, this is the answer. It's this order, n cubed. It's like I have n terms, right? I've got n terms in this sum, and the biggest one is n squared. So the worst it could be would be n cubed, but it's not as bad as it's n cubed times it's about 1/3 of n cubed. That's the magic operation test. Somehow that 1/3 takes account of the fact that the numbers are getting smaller. If they weren't getting smaller, we would have n terms times n squared would be exactly n cubed. But our numbers are getting smaller. Actually, do you remember where does 1/3 come in this? I'll even allow a mention of calculus. So calculus can be mentioned, integration can be mentioned now in the next minute and not again for weeks. It's not that I don't like 1801, but 1806 is better. Okay, so what's the calculus formula that looks like? It looks like a sum is like, if we were in calculus, instead of summing stuff, we would integrate. So I would integrate x squared, and I would get 1/3 x cubed. So if that was like an integral from 1 to n of x squared dx, the answer would be 1/3 n cubed. And it's correct for the sum also, because that's like the whole point of calculus. The whole point of calculus is, oh, I don't want to tell you, you know the whole point of calculus. Calculus is like sum, except it's continuous. Okay, and algebra is discrete. Okay, so the answer is 1/3 n cubed. Now, let me say one more thing about operations. What about the right-hand side? This was what it cost on the left side. Count, this is on A. This is A that we're working with. But what's the cost on the extra column vector B that we're hanging around here? So B, it costs a lot less, obviously, because it's just one column. We carry it through elimination, and then actually we do back substitution. Let me just tell you the answer there. It's n squared. So the cost for every right-hand side is n squared. So I'll just fit that in here. For the cost of b turns out to be n squared. So you see, if we have, as we often have, a matrix A and several right-hand sides, then we pay the price on A, the higher price on A, to get it split up into L and U, to do elimination on A. But then we can process every right-hand side at low cost. Okay, so we really have discussed the most fundamental algorithm for a system of equations. Okay. So I'm ready to allow row exchanges. I'm ready to allow now what happens to this whole today's lecture if there are row exchanges. When would there be row exchanges? We need to do row exchanges if a 0 shows up in the pivot position. So I'm moving then into the final section of this chapter, which is about transposes. Well, we've already seen some transposes. And so what's the title of this section is transposes and permutations. Okay. So can I say now, where does a permutation come in? Let me talk a little about permutation. So that'll be up here, permutation. So these are the matrices that I need to do row exchanges. And I may have to do 2 row exchanges. Can you invent a matrix where I would have to do 2 row exchanges and then it would come out fine? Yeah, let's just, for the heck of it, so I'll put it here. Let me do 3 by 3. Actually, why don't I just plain list all the 3 by 3 permutation matrices? There are a nice little group of them. What are all the matrices that exchange no rows at all? Well, I'll include the identity. So that's a permutation matrix that doesn't do it. Now, what's the permutation matrix that exchanges? What is P1, 2? The permutation matrix that exchanges rows 1 and 2 would be 0, 1, 0, 1, 0, 0, right? I just exchanged those rows of the identity, and I've got it. Okay, actually yes. Let me not clutter this up. Okay, give me a complete list of all the row exchange matrices. So what are they? They're all the ways I can take the identity matrix and rearrange its rows. How many will there be? How many 3 by 3 permutation matrices? Shall we keep going and get the answer? So tell me some more. 0. Okay, what are you going to do now? With rows 1 and 3, okay. 1 and 3. Leaving 2 alone. Okay, now what else? Switch, the next easy one is switch 2 and 3. Good. So I'll leave 1, 0, 0 alone, and I'll move number 3 up and number 2 down. Okay. Those are the ones that just exchange a pair of rows. This guy, and this guy exchanges a pair of rows. But now there are more possibilities. What's left? So there is another one here. What's that? It's going to move, it's going to change all rows, right? Where shall we put them? So give me a first row. 0, 1, 0. Okay, now a second row, say 0, 0, 1, and the third guy 1, 0, 0. So that is like a cycle. That puts row 2 moves up to row 1, row 3 moves up to row 2, and row 1 moves down to row 3. And there's one more, which is, let's see, what's left? Whoa. Is it 0, 0, 1? Okay. 1, 0, 0, okay. 0, 1, 0. Okay. Great. 6. 6 of them. 6p. And they're sort of nice, because what happens if I multiply 2 of them together? If I multiply 2 of these matrices together, what can you tell me about the answer? It's on the list. If I do some row exchanges and then I do some more row exchanges, then altogether I've done row exchanges. So if I multiply, but I don't know. And if I invert, then I'm just doing row exchanges to get back again. So the inverses are all there. It's a little family of matrices that, they've got their own. If I multiply, I'm still inside this group. If I invert, I'm inside this group. Actually, group is the right name for this. It's a group of 6 matrices. And what about the inverses? What's the inverse of this guy, for example? What's the inverse? If I exchange rows 1 and 2, what's the inverse matrix? Just tell me fast. The inverse of that matrix is, if I exchange rows 1 and 2, then what I should do to get back to where I started is the same thing. So this thing is its own inverse. That's probably its own inverse. This is probably not. Actually, I think these are inverses of each other. Oh yeah, actually, the inverse is the transpose. There's a curious fact about permutation matrices, that the inverses are the transpose. And final moment, how many are there? How many 4 by 4 permutations? So let me take 4 by 4. How many p? Well, okay. Make a good guess. 24, right. 24 p. Okay. So we've got these permutation matrices, and in the next lecture, we use them. So the next lecture finishes chapter 2 and moves to chapter 3.